Okay, welcome to the final part of this chapter. Okay, this is the third part of this chapter, and we will talk about diagonalisability. The ability. Okay, here I will just give you one definition and one lemma, and we will go straight away into tutorial. So I want to make two different videos, one for the theory and one for the tutorial, but I will combine both of them together. So this video serves as a tutorial as well. Okay. So first of all, we will explain why when a transformation is said to be diagonalizable, and when a matrix or the matrix version of that definition, and then we will see just one lemma. But let me give you the context for everything we have done so far. In the first part, we have done eigenvalues and eigenvectors. That was actually the diagonalization, because once we found the eigenvectors and eigenvalues, we can find the diagonal matrix, okay? So in the first part, we have found the eigenvectors and eigenvalues. In the second part, we have worked with the similar matrices. In this part, we will talk about diagonalizability, but this time when a matrix T is similar to a diagonal matrix. So you will be asking yourself, why are we doing all of this? It's the fact that we want to transform a matrix T, okay, which has a bunch of numbers, into a matrix that is only diagonal, that has numbers on diagonal, that has zero everywhere except from the diagonal, okay? Why? But because sometimes is not sometimes, most of the time, it's easier to understand a transformation in its diagonal form. And I'm sure, as you already know, we have plenty of applications when we can transform a matrix into its diagonal equivalence, or to a matrix that is similar to a diagonal matrix that is similar to that matrix. So basically, we want to write a transformation in such a basis that we can have only uh, diagonal numbers. You can have only eigenvalues on the diagonal. Is that okay? So that's the application, or that's the motivation or the connection between everything we have done so far. So as you can see, all of these are connected. Part one, eigenvectors and eigenvalues. In eigenvectors and eigenvalues, we have found the numbers on the diagonal, and we have also found the basis. So we can write a transformation, not anyhow, not in any representation, but we can write a transformation in a certain basis, such that that transformation is diagonal. So it's easier to understand and it's easier to manipulate. Is that okay? So this third part is going to be the application of everything we have done in part one, eigenvectors and eigenvalues, and part two, similarity. Okay, so here let's start with the definition. Okay, okay, and I want to split the board into two. So definition says the following. So let me write a small one. A transformation is diagonalizable. Okay, of course, not any matrix. Any transformation can be written as a diagonal matrix. Okay, so when we have such transformation, then we have uh, we have to meet the following condition. So a transformation is diagonalizable if it has a diagonal diagonal representation with respect to the same basis, respect to the same basis for the codomain as for the domain. So I'm sure it will remind you of similar matrices for the codomain as for the domain. This was what codomain. Okay. Two. Diagonalizable matrix. So this is going to be the matrix, the matrix version of the above definition. So dia is more practical. Okay. Diagonalizable matrix is one that is the word. This word is very important. Similar. We have seen it just a while ago. Similar to a diagonal matrix. Okay, that means T is diagonalizable. Okay, diagonalizable if there is a non-singular P such that P T P inverse is diagonal. Okay, let me is diagonal. So basically, okay, so I'm going to write D. The diagonal matrix is going to be P T P inverse. So if we can find P such that P multiplied by T multiplied by P inverse can give us a diagonal matrix. A diagonal matrix is a matrix that has entries that are zero everywhere except from the diagonal. Okay, so yeah, I'm going to give you a small note here. Okay, note not every matrix can be diagonalizable. Okay, every matrix is similar to a diagonal matrix. Okay, so let me finish the theoretical part with the following lemma, and then we will go straight away to the tutorial. Okay, so number 2, let us see the following lemma. Okay, transformation T. Okay, transformation. A transformation T is diagonalizable if and only if and only if, of course, there is a basis. If there is a basis B, okay, made of B1, beta 1, beta 2, beta n, and scalars, our eigenvalues, okay, scalars, lambda 1, lambda 2, lambda n, such that, okay, I'm sure you know the following equation, the transformation of beta I, okay, equals to lambda I beta I. You have met this equation when we were doing the eigenvectors, eigenvalues and eigenvectors. Okay, so this means the following. Okay, so we have the representation with respect to b of t is going to be equal to, so we know how to find the representation, okay, and of transformation. Representation with respect to b of the image b1, okay, up to the representation with respect to b base of t of beta n, and yeah, beta n, okay, that is going to be equal to a diagonal matrix, which is equal to the following matrix, okay, lambda 1, lambda 2, so we have 0, 0, 0. Yeah, let me do it this way. The 2, okay, and 0 here, and we have this way, 0 there, and 0, 0. Okay, so this is it. Okay, let me write my matrices better. We have here and here, there. Okay, so this is our lemma. We have seen in part 1 eigenvectors and eigenvalues and eigenvectors, that a transformation, okay, here also in this lemma we say that a transformation is diagonalizable if and only if we can find a basis and a scalar, or a basis and the scalars, such that the transformation of the vectors of that basis is equal to lambda multiplied by those vectors. So basically, we want to find a basis such that the action of the transformation in that basis is just multiplying the vectors of that basis by a scalar or by scalars. Is that okay? So let us go straight away to the tutorial so that we can apply everything we have done, we have seen so far. So the tutorial is going to be long. Okay, so because we have a lot of things to do. So let me write it down. Example. So let me write it in black. Just me being fancy here, changing colors. And so the question is as follows. So consider the matrix T, which is equal to minus 2, 0, 1, 2. And the question says diagonalize T. That means, okay, find P and P hat such that T is diagonalizable. And we have C. Okay, so let me stop here and go straight away to the solution. Okay, so here, solution. Let's do the answer here. So T, as we have seen, okay. Yeah, as we have seen in the definition, T definition, a small 2 here, T is diagonalizable if T is similar to a diagonal matrix. So that means T is diagonalizable if we can find a diagonal matrix D which is going to be equal to P, T, P inverse. So basically what we want to do is find P and P hat, multiply all these three matrices together and see if we are going to have a diagonal matrix. Yeah, and of course, yes, that diagonal matrix is going to be made of the eigenvalues, sorry, are going to be made of the lambdas, the eigenvalues, okay? So to be able to find or to answer this question, we are going to go through the following steps, okay? So step number 1. So step 1, we need to find the eigenvalues. This is how we solve such questions when you are asked to find to diagonalize a matrix. This is how you do it. Find the eigenvalues. Okay. Step 2. Now find the associated eigenvectors and just the basis. So that's how I like to write ends, but okay, if you get confused, my end is a bit funny. And thus a basis, so we can easily find a basis, okay? And step 3, find P and P inverse. So you need to go through these 3 steps, okay? So let's start here. So step 1, finding the eigenvalues of T. Okay, let me split the screen into 2. Okay, so how do we find the eigenvalues? If you remember, so basically this question is going to be made of basically everything we have learned so far from chapter 1 till this chapter, chapter 5. Okay, so it's going to be a bit long. So how do we find the eigenvalues? First of all, we need to find the characteristic equation. Okay, I can run through this quickly, but I'm going to take more time finding the characteristic. I'm sure you know how to find the eigenvalues. Characteristic equation, polynomial, sorry, polynomial, t minus x I or t minus lambda I, it doesn't matter. Okay, so t minus xi, okay, the determinant of t minus xi. So we have our t, which is equal to minus 2, 0, 1, 2. Let me check. Yeah, minus 2, 0, 1, 2. Okay, and we have t minus xi. If we don't know how to find the eigenvalues and the eigenvectors, maybe go back to the previous, the first part of this chapter, okay, our previous videos. And yeah, here is going to be minus xi or minus lambda I, doesn't matter. Minus x, sorry, just the xi or lambda I. I is the identity matrix, so we have x0, we have 2 by 2 matrix, so x0, 0, x. That means, excuse me, that means the determinant of t minus xi equals to the determinant of minus 2 minus x, sorry, 1, not 0, is 1. So we are doing minus 2 minus x is minus 2 minus x. 1 minus 0 is just 1. 0 minus 0 is 0. 2 minus x is 2 minus x. So how do we find the determinant of a 2 by 2 matrix? It's very easy. Minus 2 minus x multiplied by 2 minus x. So this is our characteristic polynomial. So after finding the characteristic polynomial, what do? We solve the characteristic equation. So we have solve the characteristic equation, which is t minus xi equals to 0. So of t, the characteristic equation of t, which is t minus xi equals to 0. So determinant of t minus xi equals to 0 means we have minus 2 minus x multiplied by 2 minus x equals to 0. That means minus 2 minus x equals to 0, or 2 minus x equals to 0. That means x is equal to minus 2, or x is equal to 2. So in conclusion, our eigenvalues are the following. Eigenvalues are lambda 1 equals to minus 2 and lambda 2 equals to 2. Okay, so step 2, find the associated eigenvectors. Eigenvectors and a basis. Okay, so how are we going to find the associated eigenvectors? So how do we do that? By solving the equation by solving the following equation. And I have explained the origin of that equation in the first part. So if you want to, if you don't remember how to do it, maybe look at my previous videos. So by solving t minus xi multiplied by beta equals to 0. Okay, so here we have a minus 2 by solving this equation. So instead of x here, let me put lambda. It doesn't matter, we can write lambda or x, but here let me put lambda t minus lambda I multiplied by beta equals to 0. And the origin of this equation, I have explained it more in depth in one of my previous videos. Okay, so we have minus 2 minus lambda 1 0 2 minus lambda. Okay, so that means we are going to solve the following equation: b1 b2 equals to 0 0. Okay, so for let me put for lambda 1 equals to minus 2, we have the following equation. The equation is minus 2 plus 2 is 0 1 0 minus 2, sorry, 2 plus minus 2 is going to be 2 plus 2, so that's going to be 4. We have 4 here. b1 b2 equals to 0 0. So this means we have b2 equals to 0, and we know how to multiply a matrix by a vector, so I'm not going to spend too much time here. Okay, and for b2 equals to 0, that means b2 equals to 0. That means the associated vector b1 b2, the associated vectors, because we have infinitely many solutions for such systems. So b1 is still b1, b2 is 0. This is equal to 1 is 0 multiplied by b1. Therefore, the associated vectors for lambda 1, so associated vectors, eigenvectors, sorry, eigenvectors for lambda 1 equals to minus 2 are b1 b2. I'm not going to have enough space, but let me squeeze in. I'm not sure. Okay, equals to 1 0 multiplied by b1, such that b1 is different from 0. We cannot have a trivial eigenvectors. Okay, so let me find, I'm not sure I'm going to have enough space here, but squeeze in. For lambda 2 equals to 2, we have the following equation to solve. So we have minus 2 is going to be minus 4, 0 here, 1, 2 minus 2 is 0, b1 b2 equals to 0 0. So that means we have minus 4 b1 plus b2 equals to 0. That means yeah, we have b1 equals to 1/4 of b2. So that means here we have our b1 b2 equals to b1 is a quarter of b2, and b2 equals to just b2. This is going to be equal to 1/4, 1 here, and b2. Therefore, the vectors associated with lambda 2 associated eigenvectors for lambda 2 equals to 2 are b1, b2 equals to a quarter, 1, and b2, such that b2 is going to be different from 0. And we can also find the eigenspaces and yeah, the algebraic multiplicity or geometric multiplicity. We have seen all of this in the first part of this chapter. Okay, so this is going to be the end of step 2. Not really. We need to find a basis. Okay, so need to find a basis. Okay, the basis B. Okay, so that basis B is equal to beta 1 and beta 2. But I will give you a quick recall, and you can skip this. I'm going to call it, change color here, and call it a quick recall of the theorem that allows us to easily find the basis once we know the eigenvectors. So recall the following theorem. And we have seen this theorem in the first part of this chapter, okay, when we were doing the eigenvectors and eigenvalues. It says, and I have done a very good tutorial about it, so don't forget to look at my previous videos. For any set of distinct eigenvalues of a map or a matrix, a set of associated eigenvectors, one per eigenvalue, okay, is linearly independent. Because to be able to have a basis, we need the vectors in that basis to be linearly independent, and we know what it means to be linearly independent, okay? And so what does this theorem say? It says that to be able to find the basis, I need to get any vector from the eigenvectors associated with the lambda 1 and any other vector from the eigenvectors associated with the lambda 2. And if I put them together, I can form a basis, or I form a basis, okay? So what we have done earlier, we have the vectors, the eigenspace associated with the lambda 1. Lambda 1 was equal to -2, is equal to, let's see, is equal to, yeah, 1, 0, b1, 1, 0, b1, such that b1 is a complex number. And the eigenspace, or the eigenvectors, okay, space associated with lambda 2, and lambda 2 was equal to 2, is equal to, let's look, a quarter and 1. A quarter and 1 multiplied by b2 such that b2 is complex number. Okay, so here, as the theorem says, let's pick any vector um, from the the first eigenspace. So for b1 equals to 1, okay, we have the vector beta 1 equals to 1, 0. And here for b2 equals to 4, let's go with the 4 so that we can have a nice vector. Beta 2 okay, beta 2 equals to 1 and 4. Therefore, according to this theorem, that means we have our basis b equals to beta 1, 1, 0, and beta 2, 1, 4. And the theorem says that these two vectors are linearly independent, and we can check it if you want to. So let me have a look just to make sure that I didn't make any mistake. Okay, so the eigenvectors here, yeah, okay, 1, 0 is with b1, that's good. Just a quick check, guys. And here we have a quarter, 1, b0, sorry, b2 is different from 0, yeah. Let's just make sure we have done everything. Okay, so that's good. I think we can continue, but as we said here, we need to go through 2 steps. We have done the first step, we found the eigenvalues, found the associated eigenvectors and the basis, and step number 3 is to find P and the P inverse. Okay, let's go. How do you find P and P inverse? Okay, step 3. Finding P and P inverse. So here, let's find P first. Or before we can find P or P inverse, let's write our diagram down, okay? So we said that, or let me say the following. Let me say this. Here we are going to consider T as the representation of the transformation with respect to the standard basis, because any matrix is the representation, we can be considered as a representation of the transformation with respect to the standard basis, because the representation with respect to the standard basis is the representation, okay? So let me write it down for you. Consider, let's consider, yeah, let me say, let's consider T as the representation, of a transformation T with respect to the standard basis E2. Okay, and here let's write down our diagram. Okay, see, T is going to be defined from C to C. Or we can say R, but when it comes to eigenvectors and eigenvalues, sometimes the scalars are not real. They are not real numbers. They can be, or the numbers can the entries can be complex numbers, okay? And sometimes you can have complex eigenvalues. So let's be safe by saying it's going to be defined from C2 to C2 instead of R2 to R2. So that's T. The transformation small t represented by big T, and with respect to E2, E2. Okay, and here we have a C2 with respect to our new basis B, and C2 with respect to B. And yeah, now we have our identity maps D and ID. We have T here, but this time it's going to, instead of writing down T hat, I'm going to write it G because we are dealing with a diagonal matrix. So here is going to be, let me change color as we have seen earlier. From up to down here, it is going to be P. This is going to be our P inverse, okay? So we can say that our diagonal matrix to get D, what do we have to do? Our D, which is the representation of our transformation T in the new basis, okay? It's equal to, we are going to go up, which is going to be, we are going to go up, so let me write it well, from right to left, we are going to go up here, which is representation of the identity map with respect to BD, okay? To be able to get D, we need to go up, across, and down, okay? Multiply by the representation with respect to E2, it's not D, I mean E2, not D, B and E2, B, E2, so representation with respect to E2 and E2 of our map T, multiply by the representation, okay, so we need to go down, we need to go up, across, and down. Down is going to be the representation of the identity map with respect to E2 and B. Okay, so now this is going to be, okay, so our D is going to be representation of the ID with respect to E and B. E2 and B is P, multiplied by the representation of our transformation with respect to E2 is T, and representation with respect to of the identity with respect to B and E2 is P inverse. So we need to find the P and the P hat, okay? We know that, so how am I going to find the P? Or let's find the P hat first. Sorry, we need to find P and P inverse. P hat. Okay, so what I'm going to do is instead of finding P, let me find P inverse. Is easier because it's easier to find the representation of the vectors of B in the standard basis. You know how? We just write the vectors beside each other. So it's easy. And I don't want to, let me go here. So let us find P hats, P inverse first. Sorry, I don't know why I'm saying P hats, I mean P inverse. Finding P inverse. It's easier to find P inverse. I can just write it down here, but since this is going to be our last tutorial in this chapter, it's a combination of everything we have done so far. Let me, show you how we can get P inverse. Let me go do the work. So we have our B, which is equal to 1, 0. You have seen our basis, and 1, 4. And our standard basis E2 is equal to 1, 0 and 0, 1. Okay, so to be able to find P inverse, which is equal, as we said here, P inverse is here, is this representation with respect to B, E2 of the identity map. So representation of the identity map with respect to B, E2. What do we do? First of all, we need to see where the identity map sends the element of B2 to. So 1, 0 and 1, 4. Under the identity map, I know this is tedious, it's just 1, 0, but it's for, explanation purposes. And 1, 4 also is going to be sent to 1, 4. Now let's find the representation with respect to E2 of the vector 1, 0. And how do you find a representation? Okay. What do? We have C1. We take the linear combination of the element of the E2. Okay, so C1, 1, 0, that is going to give us 1, 0. That's what is good with the standard basis. The representation is going to be the vector. The representation of a vector in the standard basis is going to be that vector. Okay, but let me show you the work. Okay, plus C2 multiplied by 0, 1 equals to that vector 1, 0. So C1 equals to 1 and C2 equals to 0. That means, voila, C2 equals to 0, of course, C1 equals to 0. And the representation here is, what am I writing down? We already have them there. Let's not complicate things. So C1 is 1, C2 is 0. As I said, it's easy to find the representation of a vector in the standard basis. But let me go through the steps, okay, to make things clear. Representation with respect to E2 of the second vector here, this. So I'm representing these vectors, okay. 1, 4. We have C1, 1, 0 plus C2, 0, 1 equals to our vector 1, 4. So we have C1 equals to 1, C2 equals to 4. So here we have it, 1, 4. Therefore, the representation, therefore P inverse, let me write it here. That means P inverse equals to 1, 0, 1, 4. That's how easy it is. So basically I could have done it on one line here. P inverse is going to be, I just put the two vectors of the basis B beside each other, but I decided to do the the work so that you can see where that's coming from, just for those who don't really remember how we do representation, or how do we find representations of vectors or transformations. Okay, so let me go to, we found P inverse, that's good. Now we need to find P. Okay, so finding P. How do we find P? We can find P by two options. The first option is we know how to find the P is going to be the inverse of the inverse, okay? So we can find the inverse during Gauss-Jordan, or we can find a P by doing, the same calculations which we have done for a P inverse. So let me go for, for the first option. Let's say option one, okay, using Gauss-Jordan method. Okay, so how do we do that? We write the matrix as an augmented matrix. We write P inverse because here, why are we going to use Gauss-Jordan? Because let me say P is equal to the inverse of the inverse of P. So we have P inverse already. If we invert P inverse, we will get P. Okay, so we know how to find the inverse of a matrix, of a a square matrix, of course. So P inverse is 1, 0, 1, 4. So we have 1, 0. So we have the P inverse on the left hand side and the identity matrix on the right hand side. So first of all, let us get the diagonals, the element on the diagonals into 1. So a quarter of row 2 will give us what? 1, 1, 0, and 1. Okay, so here we have 1, 0 for the right hand side, and 0 and 1 quarter. And then what we do is to be able to turn this number here to 0, we need to find to do minus row 2 plus row 1. I'm sure you know how to do Gauss method, Gauss-Jordan, so I'm going to fly through them. Okay, so 0, 1, 0 quarter here. So minus row 2 plus row 1. Here we have 1, and there we have 0. Minus row 2 plus row 1. We have 1 here. Minus row 2 plus row 1 is going to be minus a quarter. So yeah, we have here, that means P equals to the matrix here, this matrix 1, 0 minus a quarter and 1 quarter. So that's our P. Okay, let's see with option 2 if we are going to get the same thing. So we have here option 2, using the following. We say that I'm not sure I'm going to have enough space, but I'm going to squeeze it here so that we can have everything on the same page. Okay, let's find P by saying that P is equal to the representation. Let's look at our diagram again. P is the representation of the identity map with respect to E2 and B. Okay, representation of the identity map with respect to E2 and B. So yeah, so how do we do that? Step number 1, let's see where. Okay, so we are going from E2 to B. So let's see where the identity map sent the element of the standard basis to. Okay, so I know that sounds tedious, but hey, let's show it. So and 0, 1, because I wrote the element of the standard basis here. Okay, so 1, 0 and 0, 1, and 0, 1 is going to be sent to 0, 1. That's what the identity map does. 0, 1. So now let's represent with respect to B each of these vectors. Okay, so we take linear combination of the vectors in B. C1 is 0 plus C2, the second element is 1, 4, equals to 1, 0. Okay, so we have C1 plus C2 equals to 1, and C2, 4C2 equals to 0. That means C2 equals to 0 and C1 equals to 1. So the representation there is going to be 1, 0. 1, 0. Okay. So let's do the same thing for the second vector. The representation of the second vector 0, 1, second vector of E2 with respect to B is going to be equals to, we have C1 multiplied by 1, 0 plus C2 multiplied by 1, 4 equals to our vector 0, 1. So we have C1 plus C2 equals to 0, and 4C2 equals to 1. That means C2 equals to a quarter and C1 equals to minus a quarter. Okay, so let me go here. That means, so I can write the representation here. That's fine. It's equal to minus a quarter. C1 is minus a quarter and C2 is equal to a quarter. So our P is equal to, okay, the first representation is 0, 1. The second one is minus 1 quarter and a quarter. So as you can see, we have the same answers, whether we use Gauss-Jordan method or we use the representation of the identity map with respect to E2 and B. Okay, so we are nearly done. So the final answer is the following. We say that a matrix is diagonalizable if we have a D, if we can find P and P hat such that P and P inverse, P multiplied by T multiplied by P inverse equals to a diagonal matrix. And that diagonal matrix, as we have seen, is made of the eigenvalues. So that means we have this, the eigenvalue 1, 0, 0, 1, eigenvalue 2 equals to our P, which is 1, 0, which is 1, 0 minus a quarter, 1 quarter, and the T, our matrix T is, okay, I'm not going to have enough space, so let me do all of this. So we have said that our diagonal matrix lambda 1, 0, 0, lambda 1 is going to be equals to P 1, 0 minus a quarter, 1 quarter, multiplied by T, which is equal to minus 2, 0, 1 and 2, multiplied by P inverse, which is 1, 0, 1 a quarter. So our diagonal matrix is our diagonal matrix is made of our eigenvalue 1 and eigenvalue 2. So we have minus 2 and 2. Okay, so minus 2, 0 and 2. That should be equal to that. So 1 is 0 minus a quarter, minus 2, 0, 1, 2, multiplied by 1, 0, 1, 4. So that's actually the final answer. Maybe this is our final answer. Let me put it into, blue. Sorry about that, me just being fancy here. This is going to be our final answer. And if you have done all our calculations right, if you multiply these three matrices, we should get the diagonal on the left-hand side. So let us do a quick check. Let's see. Check. Let's multiply these three matrices together, okay? 1, 0. Okay, let me be more methodical here. Okay, so let's see if we will have P inverse equals to the diagonal. So P is 1, 0 minus a quarter, 1 quarter, multiplied by minus 2, 0, 1, 2, multiplied by 1, 0, 1, 4. So let's multiply all of these together. Let's keep the first matrix the same. A quarter, and multiply these two. So here we have minus 2, minus 2 here, and we have also here minus 2. We have 0 here, and here we have 8. Okay, and now multiply these two. We have here 1 multiplied by minus 2 is minus 2. 1 multiplied by minus 2, 1 minus 2. Minus 2 here, minus 2. No, I think there is something wrong. So when we did minus 2, multiplied by minus 2 is minus 2 here, minus 2, multiply by 1. Have I done everything correct? Okay, I think, okay, yeah. So here, let me check, okay, minus 2 multiplied by 1 is minus 2, plus 4 is 2, not minus 2. Is 4 is 2 here, not minus 2. Okay, so yeah. So here minus 2, okay, minus, sorry, plus 2. Minus 2 is going to be 0 here. This is 0, and a quarter multiplied by 8 is 2. Bingo! So this is our D, diagonal matrix P, T, P inverse. Yeah, that's checked. Okay, I think we are going to stop here. Thank you very much, and yeah, thank you.